High school calculus, integrals and sums. Okay, so we learned so far taking the ratio of infinitesimally small number, and this lead to when you take a limit, derivatives give you slope function. Okay, and that's about 1/4 of the calculus for 1-year class, and we cover this in a single video. Now we cover another one. If you add infinitesimally small number, infinite number, well, we write this way and take the limit n equals infinite. So what's happened to this? You're adding so many infinitesimally small number, but if you add enough infinite times, it may come to some fixed value. Okay, because ratio became slope value, right? And if the value has the variable x, then it's a function, slope function. So this was a derivative. So now we examine if you add many infinitesimally small number, it may approach to some fixed value. And what's good about this? Well, we talk about this later, the application of this concept. But this is another math concept used to solve problems. Many problems can be solved once you master this math concept. So, summation of infinitesimally small number. You have so many infinitesimally small number. The result could be diverge, the converge to a finite number, and oscillate. It may oscillate. Okay? Look at the example. Radius A, you have a circle, semicircle. Okay? You divide that into two small circles. So this is circumference of semicircle. Let's see. This is B. This is A. A equals B. Okay? And inside the B, you make another one, C, so equals C. You repeat this process, then you have infinitesimally small semicircle all together. Okay? But total length is same as A. That means if you add so many infinitesimally small number, it may reach to some fixed value, A. This is good, right? So there is a good reason to consider this type of operation. Another example, the same thing. This length, you divide into the middle point. This length will be same. if you repeat that, this length will be same. So you repeat this operation infinite times. What's happened is you have infinitesimally small triangles. You add them all, the lengths, okay? You add them all, it's become same as this length, okay? So we just made it this way or this way, but depend on infinitesimally small number. It's a triangle or semicircle, final result is different. So you cannot just assume infinitesimally small number, everything is same. They are different, okay? Because the difference come out when you add up infinite number of times. Okay, so we have to be very careful handling this situation. Now, here's a first example you can find in any textbook. Suppose you have function gx, right? And x give gx, and you take a delta x, just like the derivative, but this time instead of taking delta y, we take the area between them. So area is almost trapezoid, right? This is gx, and this is gx plus delta x, and this delta s. Delta s, this width is delta x. Okay, you use a trapezoidal area definition, which is what? Gx plus g x plus delta x, right? Delta x, that's the ds. Okay, so you add them all from value a to b, okay? Then make delta x small. When you make a delta x small, number of this infinitesimally small value become infinite number. So it's kind of represent this area S from A to B. This is a convention, okay, from A to B. So area S A to B will be like A to B delta S and the limit. If you take a limit, this approximation will reach to the final value, which is area S. Okay, so this kind of define the area of curved area surrounded by the curved line. Well, this side is straight line, but this is curved line. And we didn't have a definition of area surrounded by curved line except circle, and we had a square, rectangle, and triangle in algebra 2. Now calculus, we define the area defined by this, because what happened is if you take a limit, this approximation and area, the difference we call the error become 0. So pretty much this is going to be the area. Okay, so in the math notation, n goes to infinity, and here, and g n delta n. So we write this way: gx become fx, and fx, the top is a and the bottom is b. So this is a f is an area function. So we use s, but f x a to b is actually area a to b. Okay, so this is a kind of math notation we use, but what it's doing is to try to calculate the area surrounded by curve function gx. Get it? Okay, so this is the application. The first application we can do by this summation of infinitesimally small number, and this process we call integrating. Integrating means adding all the infinitesimally small number to come up with a meaningful number. If gx equals x, simple function, right, a to b, and gx is x, so x actually go through here. Let's see. Right? What is the area of this? Okay, so we take an integral. Now the limit n equals infinity, n a plus n delta x, because we take this delta x, the nth delta x. Okay, so we divide a to b into n. So we have a n delta x total. Okay, so in the previous video we talk about what is this and n, right? Using that formula, it's become like this. So n is number of this slice, right? So it's become like this, means 1 over 2 b square minus a square, and that's the area. Okay, so areas increase by quadratic function when function is linear. Okay, explain what fx represents gx. Well, if you remember the derivative, this is the area function, 1 over 2 x square, then gx is x. What does this mean? If you take a derivative, then same as this. Okay, so this means when you have gx, the fx is quadratic function like this. Okay, the slope of this is gx because it's a derivative. It's a derivative function. That means quadratic functions slope represent the rate of increase in the area. Rate of increase in the area. And that's what the gx is. This is the interpretation using derivatives. Okay, the interpretation using derivatives, rate of increase of area, this area is a derivative of area function. So that's what it's represent, and it's conveniently it's look like opposite to derivative. Okay, but we can say that for only some elementary function. It's not always true. Okay, so this helps to find out integral function from this function, because you just do opposite. We used to do derivative. We learned how to do derivative. We do opposite, we can get area function, which is integral function. Okay. So definition of integral is area function surrounded by a curve. We find an area function fx surrounded by this. So when you take delta x and sum them up, we slice from here 0 gx, we slice them up and add them all up to point x, then this become fx area. So that means 0 to x gx is fx. So if we take a derivative here of fx, derivatives of fx, then it shows it's the same process. It becomes gx. Okay, so when you're talking about integral and derivative, the area under the curve of function can be obtained by integrating this function. So the fx is integrating from x to gx, 0 to point x. So by taking derivative of fx, you can get this is supposed to be slope function. Okay, So that's the relationship between derivatives and integral. Okay, we practice integral. Explain we can obtain area function by finding a function whose derivative is a function that defines the area. Okay, we already explained that. Okay, so we take a derivative of integral function. Then we can write this way, right? And that should be slope function of area function. So since gx equals xn, the fx must be 1n plus 1 xn plus 1, because if you take a derivative of fx, it becomes this one. So as I said, we learn how to take a derivative of a function. We use that knowledge and figure out what that integral function is. It's look like an opposite process. Then we know how to take an integral of a function. Okay, is it complicated? If you feel this going too fast, you can stop the video and just repeat watching and digest them. Indefinite integral. Now, indefinite integral is we use this point unknown to point x. Okay, so since this is unknown, the integral unknown to x gx is fx, but there is an unknown x to unknown, which is fx plus unknown value. It's called constant value. So it's called indefinite integral because this is not decided. So indefinite integral, we simply write this way: no range a to b, no range. So it's going to be, we know it's going to be fx plus there is the unknown value c. Okay, indefinite integral practice. Okay, so this function, slope function, is ex. So integral of this is same, right? Okay, so log x, this function integral is constant, becomes 0, and this gonna be 1 over x, right? So proof is easy. You just take a derivative of the target function x. Derivative is cosine x. Okay, now integral chain rule. Now y equals f g x, u equal g x. So it's a function of function, right? How do you do that? Mathematically, we write dy dx equals, we take integral with respect to u, and we take a derivative of u with respect to x. So it's going to be integral of both function will be the derivative. So that means we have two function derivative we take an integral. This will be fg x, this form. Look at the example. U is this, so this is U. Okay, just look at the example and digest the meaning of this. This chain rule is very important for finding many types of integral. Integral formula addition. Now when we multiply constant a to the fx and constant b to the gx and take an integral of both, is same as taking integral and multiply constant a, b and adding together. Okay, so practice. Finding integral function is kind of a challenge. Like geometry, it's not straightforward. You have to try and error, and that's why finding integral challenge competitions. Like MIT, they sometimes have a student to find the integral within some time. The challenging. Here you go, more practice. Okay, and I show you the answer here. Okay, so stop the video, take the pencil and the paper and go through this. We have so many subjects to cover in this video, so the practice will be on your own. Area calculation using indefinite integral. So when you have an indefinite integral, if you bound it by area b and a, you just substitute b and a after you take an infinite integral, then you get this, right? Okay, so if you swap a and b, it's going to swap the sign, the negative, right? That's what it means here. And range must be adjusted by a new parameters. If you use a new parameter, then range has to be adjusted to the new parameter. Okay, this is like a couple days in high school math class. We use only few minutes. Area calculation. Oh, this is the fun part. Calculate a quarter circle area. Okay, function is this. The find area between cos and the sine function below. This is cosine, this is sine. What is area between? Okay, so it's going to be cos x minus sine x from 0 to pi over 2 dx. Okay, answers are here. Well, probably you have to do this practice several days after you watch this video. Volume. How do you take a volume of this kind of shape, the circle? You can do many ways. The simplest way is to take a disk, calculate the disk first. So delta y, thickness, disk, the radius is z. Okay, z is a radius, and z is a function of y, right? Function of y and delta y. So you take a integral, and if you could get the volume, then you're pretty much done with integral. Another volume calculation. Again, the easiest way is to get the disk here, and disk radius is a function of x. Okay, and that gives you the radius. So here's the answer. We give you answer. Length calculation. Now length is a little tricky. How do you calculate the length? This we call ds, the segment of the length, which is square is dx square plus dy square, and it's become more manipulative using math notation, but you get used to it if you start doing it. Look at this carefully. Length calculation. Again, another length calculation. Okay, the endless number of practice for taking integrals are in the textbook, and solving all of them takes a couple months. Okay, and that much practice are needed. Application of integral. Here we talk about another application beside calculating area surrounded by curve or volume surrounded by curve. Another application of integral is in physics. You see Newton's law. F equals ma is the acceleration, right? The acceleration is second derivative of the distance function. So velocity, to find out the velocity, we have to take an integral, and in order to find out trajectory, you have to take an integral again. So we have to take an integral twice to find out the trajectory. So that's what it is. Every mass get the constant acceleration g by gravity when the object is tossed up with the initial speed v0 for the height h0 from ground. Okay, so this is like this height h0, initial speed is v0, it goes up and come back again. Okay, so this is the distance function dt, right? So initial speed, the acceleration is gt, so the speed function vt you can calculate going back there. Okay, cannonball is shot. Okay, so this one is going up at the initial angle theta, and obtain the cannonball. Assume ground plane is x and height is y. Okay, here's the answer for you to do practice. Sorry to give you so many assignments, but that's what the calculus in the high school. Integral of hyperbolic function. How do you take an integral? Well, if you know derivative function you had already, then it's not that difficult. Derivative of inverse function Okay. Well, that was a long video. So I hope you realize you have so many assignment. The practice in calculus, derivatives and integral. Okay, that's all about the calculus. Why you do this? Because calculus is the base for every engineering problem and the science problem. Without that, well, you need to stay in sales, maybe accounting, sales, and what else? Economics. Well, economics, they use some derivative and integral these days. The modern economics, they use math theory. Okay, so that's what the calculus is about. I hope you enjoy listening, and I'll see you in the next video.